Hello, everybody, and welcome to a walkthrough of some recent research that I did with two co-authors, Tang Bui and Charles O'Neill at the Australian National University. And in this walkthrough, inspired by some of the recent walkthroughs done by Neil Nanda on papers, I'm going to describe our research and some of the methodology, sort of key takeaways, and some of the future work that could be done given what we've observed. So this is going to be sort of a casual walkthrough of the paper, and just sort of talking through our results and what we've done. And so I thought I'd start by describing what grokking is. So grokking was originally observed in the transformer architecture on algorithmic datasets. What do we mean by an algorithmic dataset? So an algorithmic dataset is a supervised dataset where you have examples and labels generated through some algorithmic process. So an example would be modular addition. So I choose a modulus of 11, and then I do 5 plus 7, and 5 plus 7 modulo 11 is 1, because 5 plus 7 is 12, minus 11 is 1. And they were saying, okay, let's train a transformer to predict 5 plus 7 modulo 11. They used larger primes, but this is a sense of what an algorithmic dataset is. And another example is multiplication modulo 11, these sorts of things. And so in the original paper, they had a look at these prediction tasks, and what they noticed is that the accuracy of the network became very high very quickly on the training set, but much later would the accuracy on the validation set become perfect as well. And so this was very interesting because traditionally one thinks, okay, as soon as my training set as soon as I'm getting good performance on my training set, I want to avoid overfitting, time to do some early stopping, and then I'm going to do well on my validation set. But not in these cases. In these algorithmic cases, you don't get this. Okay, so quite an interesting result. And since then, there's been a fair amount of work. There was been some papers showing the existence of grokking on non-algorithmic datasets, and this was achieved primarily through altering the initialization of the network, as well as a few other factors. So, with the right sort of initialization, you can get grokking on MNIST. I believe also a chemistry dataset. I think it was QM9. I could be wrong. And yeah, so this was the OmniGrok paper. Outside of that, there's been some work looking at various theories of what are the mechanisms that lead to grokking. So Neil Nanda had a look at the sort of mechanistic interpretability side of grokking. Like, okay, I have a transformer implementing this modular addition or whatever. Okay, what is actually going on in the network? And as he describes in, I think, an MLST episode, it's a bit cursed what is going on in this network. So that's one interesting side as well. And since then, there's a recent paper about the circuit efficiency. There's this hypothesis that grokking occurs as a result of the efficiency of circuits implementing different solutions in the network. There's also been some work on how training. There's been some work on something called the slingshot effect, where they notice a trend between sort of weight changes and the grokking phenomenon. And yeah, there's been a fair amount of work. One thing that we noticed that hadn't been investigated in the grokking phenomenon was its dependence on the model. So we noticed that, okay, everybody was looking at transformers. A few people were looking at neural networks. But outside of that, it was all neural sort of architectures, right, where you have some form of feature learning involved. So you could have multiple layers of abstraction, and perhaps feature learning was leading to the grokking phenomenon. Something about, these features might be leading to the grokking phenomenon. So we asked, okay, can you find cases of grokking outside of neural architectures? And so a classic, non-neural architecture is the Gaussian process. So we had a look at Gaussian process classification, Gaussian process regression, linear regression. We had a look at these cases and we said, okay, can we see grokking there? We also thought, okay, we've basically in these settings, we have an algorithmic data set, and then using that algorithmic data set, we show that the grokking exists. One of these algorithmic data sets, quite interesting, is this parity prediction problem where you have a set of bits and you want to calculate the parity of those bits, but then you also give the network some random bits as well. And we noticed that as you change the number of random bits, you would actually get more and less grokking, and that this addition of random bits induced grokking in every sort of algorithmic data set we tried. So the first thing we noticed is that grokking occurs outside of neural networks, and the second thing that we noticed is that there's actually this data augmentation technique where you add these random bits and you produce grokking. And so, we noticed these things, and then we started having a look at the trajectories of training through the weight space of these different models. So we had a look at a Bayesian neural network, and we had a look at a Gaussian process regression model. And we said, is there anything that is common to these trajectories that could explain grokking in this new setting? So this new setting being grokking in non-neural architectures, because the previous theories had really worked on this idea that it really sort of in the context of neural networks. And so we asked, okay, can we abstract it a little bit and try and formulate a new theory based on our new observations? And I think, our theory it seems like a reasonable hypothesis given the observations we currently have. It seems like a reasonable explanation of grokking in these new settings. Of course, there could be other examples of grokking. There could be other ways that grokking might occur, but this seems like we think we've developed a fairly reasonable hypothesis as to what's going on. Okay, now that we've described the sort of the narrative of the paper and how the research was completed and sort of our main takeaways, I'm going to discuss the methodology, our main results, and some future takeaways. What I'm not going to do is I'm not going to discuss in detail the theoretical sides, which we write about in the paper. So there is a talk in the introduction about generalization, about model selection and complexity, different notions of complexity, how these different notions of complexity influence, how these different notions of complexity line up with the different models that we use and the different loss functions that we use. These I will leave to you if you're really interested about them. It's a bit of a mouthful to explain in a paper walkthrough, so I'm just going to stick to the meat, which is the results and the methodology and some takeaways from those. But I encourage you to have a look at the theory side if you're really interested. I think it's quite interesting to look at different ways of unifying different measures of complexity and how we might do that under different models. And I think we give a fairly good explanation of model complexity and how one uses model complexity to decide upon a good model for the data. And so all you need to know sort of for this walkthrough is that many loss functions have an error term and they have a complexity term. And our theory of grokking has to do with the interplay between this error and this complexity. So looking at this error and looking at this complexity, we notice that there's sort of you can classify different regions according to whether they're high error, high complexity, low error, low complexity. And cases where you see grokking correspond to different trajectories through these regions. And that's basically sort of our hypothesis, our effective theory of grokking, is that different regions in the error and complexity landscapes result in different trajectories and thus result in grokking or not. And so for the purposes of this video, I'm going to leave more detailed discussion of error complexity to the paper. Okay. So on to our results. So the first thing that we looked at is grokking in non-neural network architectures, specifically GP classification and linear regression. And so for linear regression, we completed classification on something called what we called a 0-1 classification task. And so in the 0-1 classification task, we essentially have a line like this. It's like y equals 0.3x or something like that. We have a line like this, and then all the regression is going to do is going to predict whether a point is positive or negative given the x value. So, given x equals 0.5, because you have a line like this, it should be positive, so on and so forth. But we give we augment the network with spurious features. So we add these sort of spurious features to the input, and we also change the weightings of these features. So the main important feature is the first, because given a line like this, you can simply predict whether it's positive or negative based on this value. But because we downweight this value and we upweight other sort of spurious features, although the cubic should lead to, you could just predict positivity from the cubic. This leads to other, this leads to grokking, because we sort of augment our situation by adding these spurious features, and then we just sort of complete learning as normal with a regularization term and a mean squared error. And what we find is that we get grokking. So as you can see here is the training accuracy over the number of epochs, and then the validation accuracy is in blue. And as you can see, the training accuracy gets to quite a high value fairly early in training, and then the validation accuracy gets to quite a high value later in training. So, okay, maybe this doesn't, if you're a real hardliner, okay, it should be 100% accuracy. In the appendix, we provide a case where you do get 100% accuracy in the validation. It's not just, 0.99, which it is, and 0.98 in this case. And so that was our setup for linear regression. And so what's interesting about this is really quite a basic sort of situation. We're doing prediction on a slope. Okay, we've added some spurious dimensions to the input, which don't have specific relevance to the prediction task. And then we're simply predicting whether things are positive or negative. And in that case, if you restrict sufficiently the number of training data points, you get this grokking phenomenon, which is fairly interesting. And this, there isn't sort of a higher order prediction prediction that's going on. There's one layer, it's a linear regression, and yet it still exhibits this grokking phenomenon, which I think is quite interesting. Also of note is if you look at the data fit and the complexity, the data fit goes to zero, or not zero, but sort of goes down and then plateaus quite quickly. But as the data fit is plateauing, the training complexity then sort of the main bit of change for the quite a lot of change of the training complexity comes after the data fit has plateaued. And it seems, if you look at this, it seems that this training, like the minimization of the complexity rather than the data fit, is leading to a increase in the validation accuracy. And so one might say, okay, well, we start off in a region of high complexity and high error. We end up in a region of low error, high complexity fairly early in training. And then from low error, high complexity, we transition into an area of low error, low complexity, and that is what drives up the validation accuracy. So that's just a note for later. Okay, and so that was linear regression. I think it's fairly interesting that in this fairly, it's not particularly complex, you get something which I would call grokking, something which I think has this interesting property that you get high accuracy early and high training accuracy early and high validation accuracy later. It has this interesting property. Okay, so then we moved on to classification with the Gaussian process. So we had a look at two different data sets. So we had a look at a 0-1 classification task, which is described in data set 8. So in the 0-1 classification task, you simply are trying to distinguish whether a point is 0 or 1. So a point is above 0 or if it is below 0. And so if it's above 0, then it should be positive, and if it's below 0, it should be it should have a classification of 0. And so you normally distribute these points, and then you see whether they get labeled correctly. And so in this basic classification task, you see what I think is interesting. It's not perfect accuracy, something like 97% accuracy, but you see early high training accuracy and later high validation accuracy, as is the case in Grokking. And then finally, for the Gaussian process, we had a look at the parity prediction task. And in the parity prediction task, as I think I mentioned before, there's a small number of bits for which you want to predict the parity, and then a large number of additional sort of random dimensions. And in this case, we get this sort of canonical, beautiful example of Grokking where we have very high training accuracy very early, 100% training accuracy early, and then high validation accuracy much later. So I think this shows in the case of linear regression and one of the GPs, you might argue, one might argue that it's not in the most strict sense Grokking as identified in the original paper with 100% accuracy. But I think those two cases represent something interesting and represent a Grokking, what I would consider what's interesting about Grokking, which is this high accuracy early on the training set and high accuracy later on the validation set. And certainly with the case of the Gaussian process classification on the parity prediction problem, you get 100% a case of Grokking. And so this shows that Grokking occurs outside of neural networks, and with a radial basis function Gaussian kernel, we don't have a neural kernel, this is a radial basis function Gaussian process, we get Grokking on these data sets. Okay, so that's one of the main points of the paper is Grokking outside of neural networks. Moving on, having looked at Grokking in non-neural network cases, we then returned back to looking at the data sets on which Grokking has been found to occur. And there is this world of non-algorithmic Grokking. We didn't have a look at that. We simply looked at algorithmic cases and ways of augmenting algorithmic data sets to get more and more Grokking. So we asked, if you just add these random dimensions with any algorithmic task, if you just added these random dimensions, would you get more Grokking? And the answer is yes, you do get more Grokking. And so figure 4 here is an example. So we had a look at these 6 different tasks, and we said, if we add, say, 10 spurious dimensions, 20 random dimensions, 30 random dimensions, 40 random dimensions, do we get more and more Grokking? And in fact, we do get more and more Grokking. The gap between the high training accuracy and the high validation accuracy gets wider and wider as you add more spurious dimensions. And we'll see later how this can be explained using our effective theory of Grokking. Okay, so we had a look at Grokking and non-neural networks. We had a look at how we might augment a data set to induce Grokking. Then we started thinking, how can we explain these new observations? And so to do that, we had a look at the training trajectories of these models. So we started by looking at a Gaussian process, completing a regression task. So this was regression of a sine wave, which is a noisy sine wave, where the optimization, where the loss and the sorry about that. Okay, beautiful. So we looked at GP grokking on a sinusoidal example, so where it was trying to, additional points were added sort of on the sine wave, and we were trying to predict, we're trying to predict basically sort of the validation points, which were also drawn from this sinusoid. And here the data fit term and the complexity term are defined as normal. So the data fit term is this, and then the complexity term is this usual sort of log kernel. And if you look at the data fit, which is sort of the error, which is corresponding to the error, and the complexity, which, in a neural network is sort of like the complexity in the neural network is the weight decay. In a GP, it's this log kernel thing. If you have a look at that, and you have a look at the marginal likelihood landscape, and one is seeking to, minimize, one is seeking to maximize the likelihood. So one is seeking to minimize the negative marginal log likelihood. Okay, anyway, so if you look at the training trajectories in these cases, if you look at the training trajectories in this Gaussian process regression case, you see several different outcomes depending on where you start the model. So in this figure, we have 3 different model initializations. So in initialization A, as you can see, we start off in a region of high data error. So we start off in a region of high error and of low complexity. And what we see is just a normal training curve, basically. Like, suddenly we go into the low error region and it's low complexity, so the training and the validation sets should have sort of similar error, and they do. In B, we start off in a region of low error, high complexity, and what we see is a clear case of grokking. The low error, like it's low error immediately, and then much later do we get low validation error because the complexity has decreased. And then finally, with model initialization C, where we start off in a region of low error and low complexity, well, we've solved the task. And so this was interesting. Okay, this happens in the Gaussian process regression, where we have this high, we start off in these different regions and they lead to different training curves, with one leading to this grokking type training curve. Could there be a trend here? So then we had a look at a Bayesian neural network, and we had a look at the Bayesian neural network on the parity prediction problem. And what we saw some interesting results here. So we also saw that let me a little refresh here. Yeah, what we saw is that so there's 2 things to look at. So in the leftmost graph, what we see is different trajectories through the error and complexity landscape. And so the complexity increases on the left-hand side and the error increases on the right-hand side. On the bottom, the error is increasing and complexity is decreasing as you go down. And what you notice is that if you start out in a high error, high complexity region, you then go into, start out in a high error, high complexity region. That is the last model to grok. And so all of these models are being drawn to this low error, low complexity region. And it's in this region that they grok. And so it's a matter of how long it takes to get to this low error, low complexity region, and how quickly you're in a low error, high complexity landscape. And this is also what we notice here is that firstly, models are drawn to this low area, low complexity landscape as they should be via the optimizer, and that if you start out in a higher complexity region, you then grok later with these triangles. These triangles represent when grokking occurs. And if you sort of average over these different initialization schemes with the Bayesian neural network, you see that the error and complexity take this same route in every case. You have the average error, which decreases early, and then you have the average complexity, which decreases later. And it's only after the decrease of the complexity, once the error has plateaued, that you then get grokking, which is this line here, which is the dotted line. So this was quite interesting, and this leads us to our theory of grokking. So in our theory of grokking, we claim the following. If the low error, high complexity weight space is readily accessible from typical initialization, but the low error, low complexity weight space is not, models will quickly find a low error solution which does not generalize. Given a path between a low error, high complexity and low error, low complexity region, which has non-increasing loss, solutions in regions of low error, high complexity will slowly be guided towards regions of low error, low complexity due to regularization. This causes an eventual decrease in validation error, which we see as grokking. So here we have this classic case as in the GP regression, where in B, we start out in a low error. The low error, high complexity region is readily accessible because we've been initialized there. And then after that, we slowly move into the low error, low complexity region guided by regularization. And then it's only after we walk and walk and walk towards this low error, low complexity region do we finally grok. And what we notice is that this happens in a non-neural network case and a neural network case. And so this is our hypothesis of grokking in this more general setting. And we think that it's fairly congruent with existing theories of grokking. Something like circuit efficiency, that is congruent with our theory because efficiency, like sort of circuit efficiency, in some sense, a more efficient circuit is less complex. It's a less complex description. What we mean by efficiency is tied to complexity. Yes. Okay, so yeah, this is our theory of grokking and what we think it might be a reasonable hypothesis of the phenomenon. And in the paper, we talk about how this describes previous empirical results and how it describes the new empirical results. What I wanted to mention is that two things. Well, firstly, that this theory of grokking, which has to do with the accessibility of these different regions, is model agnostic. Like, it doesn't really, as long as your model optimization is guided by both error and complexity, you can have, as long as you're guided by both error and complexity, you can have grokking, right? A human guided by error and complexity may exhibit grokking under this sort of theory. And that's why it can generalize past the neural network case. The second thing, so that's why it's congruent with our sort of neural network observations. The second thing that was interesting was this data augmentation stuff, where we're looking at the number of additional dimensions. We're looking at the additional gap, the grokking gap that's induced. And what's interesting here is that it actually seems to be a fairly exponential trend. And we talk about this in the appendix, our regression coefficients, etc. It seems to be like the exponential trend seems to explain the data quite well. And in that case, what's interesting is that sort of this exponential increase, we also know that if you look at sort of regions inside of the weight space describe it here. So, we know that, say you have a region in an n-dimensional space, and you have a look at the volume of that region. We know that decreases actually exponentially as we increase n. And so it seems like a big coincidence that that's the case. And we also see, as we increase the dimensionality here, this what looks like an exponential trend with the Grokking gap. And so maybe there's something there in terms of how the weight space increases exponentially and what effect that has on the amount of time it takes to go from a low error, high complexity region to a low error, low complexity region. We need to sort of think about this a little bit more, and it might be an interesting next area of research. Of thinking at least. I mean, I don't know if it's worth, how much it's necessarily anyway. Okay, and so hopefully that has been a useful summary of our methodology and results. So hopefully that's been a useful summary of the methodology and results. I'm now just going to talk about briefly sort of what we could have improved on in terms of, where were some of the caveats in some of the stuff that we had a look at, and where might one look to in the future in terms of future work. And so there are a few things. So one thing that was that might have been improved was more on the theoretical side, and this was talking about how we unify different measures of complexity. As it currently stands, we look at error and complexity as these two terms in a loss function, and whenever you have complexity and error in a loss function, you can then get grokking under our theory. But perhaps the class of loss functions which exhibit grokking is more restrictive. Like perhaps there's a certain one needs a certain form to the complexity and the error to realize grokking. Maybe there's some unifying complexity measure which results in grokking. It could also be the case that one doesn't need complexity at all, and this is maybe just this may just be a single avenue to grokking, and there may be other avenues to grokking. There was a recent paper which had a look at this. So they looked at grokking, and there didn't seem to be any regularization. There was no mini batch, there was no L2, etc., and they seem to find grokking, although I haven't looked through that paper in detail. So that's quite interesting. And so there's lots of other things that we can point to in terms of our theory assumes this error and complexity decomposition, and it's the sort of interplay between those two. Perhaps this is just one route to grokking, or perhaps this route is too general. Maybe there's a more specific route that we're actually uncovering here, and that there's some similarity between the complexity in the GP case and the complexity in the neural network case that we haven't teased out, that could be leading to grokking, and that in other error and complexity landscapes, without this similarity, one wouldn't see grokking. There are different sort of critiques there in terms of the specificity of our theory, the generality of our theory, that sort of thing. Another point on this complexity stuff has to do with the way we measure complexity in some of the GP cases. So we didn't use an exact GP inference in every case. We used a sort of variational approximation in a few cases. And with the variational, with the evidence lower bound minimization process, the KL divergence, which is typically synonymous with the complexity, is not always because both the prior and the variational approximation, so because the variational approximation is changing, you don't always have the same prior that you are comparing to, and as a result, your variation, like your complexity measure, is changing over the course of optimization. So you don't have a consistent complexity measure, and so because of that, we couldn't provide. Well, we did. We provided them in the appendix, but we didn't necessarily have clear observations of the complexity in the GP case in everything that we tried. So that was another point of critique. In terms of future work, I think it would be really interesting to think about modeling, whether you could expand the set of models further. Could you look at decision trees or something like that? Another interesting point would be, looking at this question of, can we maybe formalize the theory a little bit more? Can we look at perhaps maybe there's some sort of set of mathematical, much more sort of clear mathematical statements we can make about the probability of grokking given a certain complexity measure and a certain loss. Perhaps there's some formalism that can be introduced for this particular type of grokking, for the grokking that we've outlined here and for our theory of grokking. But yeah, I think sort of the main takeaways from the paper, I think it's interesting that grokking occurs outside of neural networks, and I think any new theory of grokking, if needs to account for this. I also think that this sort of data augmentation is quite interesting and might even be a route to grokking, a different route to grokking in non-algorithmic cases. Perhaps this sort of data augmentation could lead to grokking in, say, MNIST or something like this. Yes. Okay. Well, hopefully that sort of casual discussion of grokking made some sense. I thought it would just be interesting to produce a video sort of explaining the paper in words and what I thought the main takeaways were. If you have the time, I'd encourage you to have a look at the paper and for more of the theoretical aspects in terms of how we define complexity, and a bit more how do we actually define grokking such that grokking is what we see in these cases, and a little bit more on the detail oriented side. But yeah, I guess that's all I want to say. And if anybody got to the end of this, thank you for watching.